Today, we are going to decode one of the most complex pieces of machinery on the planet, the helicopter engine. We'll see how a team of researchers found a truly revolutionary way to design them, not from scratch, but by unlocking secrets hidden in over 70 years of data. So let's get right into it. Just look at this thing. It's an absolute masterpiece of engineering. Every single pipe, every gear, every valve. It's all the result of 1,000 different decisions, and each one affects every other. But that brings up a really fundamental question.
I mean, when you're just staring at a blank page with no engine in front of you, where do you even begin? Well, that's the exact puzzle we're going to solve in this explainer.
Okay, so here's our roadmap. We'll start with the engineer's big dilemma, then uncover this decades-old problem of a missing blueprint. We'll see how researchers cracked the code with data, which led to a new design shortcut that they put to the test on a very famous engine. And finally, we'll talk about why this all really matters for the future of flight. First up, let's talk about the sheer complexity of the design challenge itself. This really is the central dilemma that every single engine designer has to face. You know, the key thing to understand about a helicopter engine is that it's not just a collection of independent parts you can bolt together. No, it's a deeply integrated system. Think of it like a spider's web. If you pluck one single strand, the whole web vibrates. And this slide shows that web perfectly. Say a client comes to you and says, "I need more power." Well, an engineer can't just make one part bigger. That one change immediately impacts the engine's weight, how much fuel it guzzles, its physical size, and even how hot it runs. It's a constant, delicate balancing act. And hey, this isn't just a metaphor. The source paper we're looking at today puts it perfectly. All these interconnected parameters create, and I quote, numerous limitations. In other words, you're forced to design inside a very complex, very constrained box. So if the design is that complicated, you'd think engineers would have decades of shared knowledge to lean on, right? Well, that leads us straight into our second big problem, the missing blueprint. For a long, long time, designers were pretty much working in the dark. So any engineering design process starts with what's called the conceptual design stage. And here's the really crucial part. It all kicks off with an initial guess. You plug in some starting numbers for things like size and airflow, and then you just run calculations over and over and over, refining that guess until the design finally works. But here's the kicker. What happens when you don't have a good reference point for that all-important first guess? How do you even know if your starting numbers are in the right ballpark? This was the exact roadblock they were facing. And here's why. For decades, all this crucial data was locked away. Manufacturers guarded their designs as top trade secrets, and governments classified anything related to military hardware. So there was no shared blueprint, no central library an engineer could check to make an educated first guess. This brings us to the breakthrough moment. The researchers realized that if the blueprint they needed just didn't exist, well, then they were going to have to build it themselves. That's right. Instead of just waiting for the data to magically appear, they took matters into their own hands. They set out on this massive mission to collect, organize, and analyze every piece of public information they could possibly find on helicopter engines. And the scale of this effort was just huge. They put together a unique database covering 132 different turboshaft engines. That's the specific kind used in most helicopters. They pulled data from the earliest models way back in the 1950s all the way to today. It was basically a 70-year history of engine evolution, all in one place for the very first time. And as they sifted through all this historical data, they started to see these amazing patterns emerge, what they started calling hidden rules. These were like the unwritten laws of engine design that had developed organically over decades, but had never actually been written down or mapped out. And this is a brilliant example of one of those rules. They figured out that if you know how much power an engine needs to make, you can predict with incredible accuracy how much air it has to suck in every second. That's its air mass flow. It was this direct mathematical relationship that was hiding in plain sight the whole time. So what do you do with these hidden rules once you find them? Well, you turn them into a tool. This next part is all about how they transform that raw data from just an interesting observation into a really powerful new design shortcut. By analyzing all those patterns in the data, they were able to convert these hidden rules into a set of powerful formulas. So now, instead of just guessing, a designer could plug in their desired power output and get a highly accurate estimate for another key parameter, like the engine's size or its airflow. The guesswork was basically replaced by math. And this new process is a total game changer. You start with the one thing you know for sure, how much power you need. Then, you use these new data-driven formulas to get a fantastic first guess for everything else: the size, the weight, the airflow. This makes that final refinement loop incredibly fast and way more efficient. Of course, a model is only as good as its results, so the next logical step was to put it to the test against a real-world iconic piece of engineering. Let's call it the Black Hawk test. The test subject was the legendary T-700 engine. Yup, the workhorse that powers the famous Black Hawk helicopter. The researchers basically asked, if we were designing this exact engine today, using our new model, how close would our numbers get to the real thing? And here are the results. Just look at this. Their model predicted the engine's diameter with 93% accuracy. For its length and weight, they were 96% accurate. I mean, think about that. An error margin of just 4% on the weight of an engine this complex, based only on a formula they derived from historical data? That's incredible. It absolutely proved the model worked. Okay, so we've seen the problem, the data-driven solution, and the proof that it works. So let's wrap up by zooming out to really understand why this matters for the future of engine design. At the end of the day, what this all really means is that a better starting point lets engineers spend less time guessing and more time innovating. This leads to faster design cycles, which lowers development costs. It frees them up to experiment with new ideas, and that paves the way for the lighter, more powerful, and more efficient engines that are going to power the next generation of aircraft. You know, this entire process was about reverse engineering 70 years of design evolution just to find its hidden logic. And that leaves us with a really fascinating final thought. If analyzing the data of the past can so accurately recreate what we've already built, what entirely new possibilities can it help us build for the future?